Hello everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through this 9701. It's a Cambridge International A-Level for the June 21, paper 1-3. So it's a multiple choice component paper that covers the entire AS level chemistry, spanning the 3 branches of chemistry, the physical, the inorganic, as well as the organic paper. Okay, so in this kind of restructured tutorial, so you will see that I don't portray the question paper anymore, but I'm pretty sure you know where to find the question paper, provided you know the code number. I'm not going to tell you how to find them. You should be able to find them yourself. And before I start, there's a button on the bottom right for all my tutorial videos on my channel, so do click on that button to subscribe to the channel and follow me at ptet.chemistry. There is the background watermark, so you should be able to find me across the various social media platforms. And in the future, the channel will have membership perks, meaning to say some tutorial videos will only be available to channel members. Okay, anyway, so let's get started with this paper. In this question 1, excuse me, in this question 1, we have an organic compound X, and we know that there is a certain percentage of carbon, hydrogen, oxygen, and chlorine. These are percentage by mass. So percentage by mass is out of 100%. So you could imagine them as the mass out of 100 gram. So this is also equal to mass per 100 grams. So if you have 100 gram of the substance of X, then that means 30.6 grams is going to be carbon, and 3.8% for the hydrogen, 20.4 and 45.2. If these are the masses, then you can work out the mole. So going straight to your periodic table, so mass over the relative atomic mass from the periodic table, that will give you the mole. And then just press it onto your calculator to work out the mole. What is very important that a lot of students they just do their working without really labeling stuff, and that is one of the biggest danger you can ever do. Whenever you are doing something, you thought you are doing the working fine, but then let's say 10 minutes later or half an hour later, you finish your paper, you want to check your work, but you forgot what you did earlier. So there's a whole beauty of actually writing down the working, so that everything fully labeled, so that you know what you are doing. Okay, what I'm going to do next is basically finding the simplest ratio. The simplest whole number ratio is going to be whatever the smallest number. That's what we're going to divide that by. So that is divided by 1.275. Actually 1.27 is smaller, so I'll divide by 1.27 actually. So 3.8 divided by 1.27. So give or take, I mean, some number is going to be not exactly whole number. So we have to try and work it out. So I get that to be 2.01. So that's 2.99. And that should be close to 1 because the numbers are pretty similar. So these numbers are very, very close to their nearest whole number. I can round it up to 2. In certain cases, you cannot round it up just like that, especially when you have, let's say, 1/4, 1/3, 1/2. This is around 0.5, this is around 0.33, this is around 0.25. When you have these decimal numbers, you have to multiply by these certain numbers to get them to the nearest whole number, just to be aware of this particular thing, that is, it has to be the simplest whole number ratio. So looking at that, we have our empirical formulas, C2H3, what's the third one, O1 and Cl. So C2H3OCl, there's option A, which is our answer there. Question 2, so looks like we have a combustion analysis. So these are gas volume, reacting volume kind of analysis. You should be able to find this in my topical playlist under the mole and stoichiometry for the A-level topical playlist. So what do we have? We have propane, and they are burnt in excess oxygen. So we have to construct a balance equation for this. I put down straight away 3 CO2 because 3 carbon from the hydrocarbons will give me 3 carbon for the carbon dioxide, and it's complete combustion because it's in excess oxygen anyway. So hydrogen, so there's 8 hydrogen, I should have 4 H2O. Now the last bit is just to balance the oxygen. 3 times 2 is 6, and then 4 times 1 is 4. 4 plus 6 should be 10, so that will give me 5 O2 there. What else do I have? I have a mass of 9.61 gram. And what volume of carbon dioxide is produced. Okay, so I want the volume, and all of these are in dm cube. I also know that the molar volume of a gas means it's the volume of a gas for 1 mole of any gas at room temperature and pressure, as given in your periodic table, as you have learned this from your O-level or IGCSE chemistry. So the mole of CO2 is to the mole of C3H8. It's going to be 3:1 from the balance equation. 3 mole of that and 1 mole of that. People have asked me, does it matter which way around it is? It doesn't. If you get it the other way around, then you have 1/3. These are all mathematical. Whatever is on top, you put it on top. It depends on what you have labeled. This is carbon dioxide, so there is volume of gas. So I will have the volume of CO2 divided by 24, because I want the mole of CO2 and I want the volume in dm cube, so I use 24 dm cube per mole. Okay, at the bottom will be the actual mole of the propane that I'm burning. I'm given the mass of the propane. So realistically speaking, given the masses, I have to work with the MR. So there's 12.0 times 3 plus 8 times 1.0. So I get 44.0. Your calculator will show you 44, but I know better because I've used the A-level periodic table that gave me the relative atomic mass to 1 decimal place. These are the kinds of accuracy that you should be accustomed to. These are what you call appropriate number of significant figure, as you are, well, as stated in the syllabus in the first topic, the mole calculation and stoichiometry bit in the syllabus. They just don't put it out directly like that, but you should be able to appreciate what they want you to do, which is to develop decision making based on, well, all those experimental techniques that involve calculations and stuff. Yeah, so 3 times 9.61 divided by 44 times 24, I get 15.725. So looking at the answer, 15.7 dm cube seems to be sensible, and this is option, oops, I don't mean that. This is option D. Okay, and there will be in dm cube because of how we have set up the formula to be volume of the CO2 in dm cube divided by the molar volume in dm cube per mole. Question 3, so this is about counting electrons. So, I mean, with every question, you gotta know how to unlock the questions. Counting electrons is to do with atomic structure topic. Even year 9 students should be able to do this, so you need to be very careful. Ammonium ions is NH4 plus, okay? So it's got nitrogen forming a dative covalent bond. So you got a lone pair on the ammonia molecule, and what happened is you can form a dative covalent bond, and that is your ammonium ion. And now it's 109 degree because previously it's got 1 lone pair, but now it has got 4 bond pair and 0 lone pair. What happened is the 4 bond pair repel equally. This question is not about shape of molecule, it's more about, well, shape of molecule or shape of ions, but it's more about the counting the number of electrons. Okay, so 109 degree or 109.5 degree, that would have been okay. Anyway, so let's have a look. What do we know? We know that we can count one by one. So count the protons first, the number of protons. So I have 7 protons because this is not relative atomic mass. This is counting the protons for the nitrogen. I have 4 hydrogens. So I have 4 times 1, which is 4 protons for the 4 hydrogens. So altogether, total number of protons is going to be 11. But then my total number of electrons should be equal to the number of protons if I have no charge, but I have a +1 charge, so I took away 1 electrons, and therefore I now have 10 electrons only. And overall you can see I have 1 extra proton than electrons, that's why I have extra +1 net charge. Okay, so what happened then is we are looking at something that has 10 electrons, and they are looking at atom. So the question says atom. Atom meaning number of protons equal to number of electrons because they are electrically neutral. Magnesium has got 12 protons, therefore the electron is 12. Sodium has got 11 protons, so 11 electrons. Neon has got 10 and 10. I think we've got our answer, which is neon. Just to complete the story, oxygen is 8 and 8 because these are all atoms. So follow the proton number and you get the number of electrons. So the answer there must be option C. Okay. Question number 4. Oh well, this is about shape of molecule. I was just talking about the importance of counting bond pair and counting lone pair. This is a concept called valence shell electron pair repulsion theory. So I did actually make a tutorial video on explaining VSEPR a long time ago. I don't think I have added it to the tutorial topical playlist yet, but I will do that very shortly. You should be able to find it on my channel. Okay, let me just draw out what we are supposed to label so that we will have better idea of what they want us to do. Okay, so they purposely make it drawn in such a way that you might interpret the diagram literally rather than thinking about VSEPR. There's always a difference between the people who are prepared for chemistry or not. Okay, VSEPR, you got to count bond pair, bonding pair, and also lone pair, and then know the shape. Okay, and therefore the geometry, basically the shape and the bond angle. They've drawn in such a way that this looks like 90 degree, this looks like 90 degree, this looks like 180 degree, but that's not always the case. You have to count. Okay, so around the carbon, how many bond pair are there? You count the sigma bond, which are the single covalent bonds. 1, 2, 3, 4. So there's 4 bond pair. And how many lone pairs are there? Carbon has got 4 outer shell electrons, 4 valence electrons. Use 1, 2, 3, 4. So no more lone pair. Around this carbon, I'm talking about this carbon now, so perhaps I should use a different color just to be safe. And yeah, okay, so I've got 1 sigma because this is a double bond. So when you have a double bond, you have 1 sigma and 1 pi. This come under covalent bonding topic. So 1 sigma, 2 sigma, and 3 sigma. So you got 3 bond pair. You also have 0 lone pair because these carbons 1, 2, 3, and 4. There are 4 covalent bonds. The carbon has used all the outer shell electrons to form covalent bonds. Oxygen, on the other hand, for this one, so oxygen is in group 16. It's got 6 valence electrons. It formed 2 covalent bond there, so 2 sigma. But you only use 2 out of the 6 for covalent bonding. You still have 4 more electrons, which is correct, but this is a lone pair, so there's 2 lone pair because there's 4 electrons not used for bonding. So what happened then is we got to work out the shape, and as you know, when you have lone pairs, the lone pair will repel more than lone pair bond pair, which repel more than bond pair. So lone pair repel more than lone pair bond pair, which repel more than bond pair. So this is greater repulsion. It's all about the repulsion that forces the atoms to have to get pushed down a little bit. So here your shape is going to be tetrahedral. Okay, I beg your pardon, I've used a different color. Perhaps I can just use black just to be consistent throughout. And then the other one is going to be trigonoplanar. Of course, all these things are actually running through your mind. So this is bent. I think some books call it nonlinear, some books call it V-shape. I typically just use bent, and that has never created me any problem at all. Okay, so the bond angle for tetrahedral, 109 or 109.5, 120 degree for trigonoplanar, 104.5 degree for the bent. Now increasing bond angle. So this is X, Y, and Z. So in the order of increasing bond angle, you want it from smallest to biggest. So there's going to be Z, and then going to X, going to Y. So Z, X, and Y. There's going to be option A there. Question 5. Question 5 is about bonding, structure and bonding. What do we know? Quite a lot of words. All right, so let's have a look at substance 1. So substance 1, strong covalent bonds between atoms. But then you have covalent bonds between atoms. So that is typical of a covalent compound. And then you have this thing called permanent dipoles between molecules. This is very important information because it means the molecule is polar. These are intermolecular forces. So this permanent dipole is what you call intermolecular forces. And the fact that you have permanent dipole, therefore the molecule 1 is polar. So there is a net dipole moment. So this is the AS concept, net dipole moment, because the dipoles do not cancel out. If you look at the option, I can tell you that option D is out because CH4 is non-polar, as all the atoms are hydrogen in a tetrahedral setting, and therefore the dipoles cancel out. The other one where it's non-polar will be Al2CO6 because because what you have really is you have a symmetrical environment. Think about symmetrical distribution of charge. So obviously one of these is a dative covalent bond, and that is a dative covalent bond. It doesn't make a difference because it's tetrahedral throughout, and you have the same number of atoms around that aluminum with no lone pair, resulting in a unsymmetrical distribution of charge. Here these are all non-polar because their distribution of charges is going to be symmetrical, and therefore they cancel out. So looking at that, option B is also out. So I'm left between option A and option C. So let's have a look at substance 2. Substance 2, I have weak forces between molecule. So again, I have a covalent compounds because they say covalent bonds between atoms, but they say weak forces between molecules. So why in the world did they not mention permanent dipoles? Because the weak forces there would most likely point towards just van der Waals, so meaning to say non-polar, because there's no permanent dipole. So we are looking at something which is non-polar. So like I said, just now D and B are crossed out. So I'm looking at options A and option C. So am I correct? Let me see. I might be wrong actually. B and D is out. B and D is out. Al2CO6 and CH4. Al2CO6 and CH4. I think I must be wrong then, okay? It means that Al2CO6 must have a little bit of oh well, actually I might be correct because I did say they are non-polar, right? So in substance 2, so we're looking at substance 2, beg your pardon. So substance 2 for A is Al2CO6, that is going to be okay. For C, CH4 is going to be okay because these are non-polar, which means there's nothing that can allow us to decide until we look at the property of substance 3. Substance 3, it has hydrogen bonds. So all of these are covalent compounds, but substance 3 has hydrogen between molecules. So looking at substance 3 for A and C, we have A, which is CH2Cl2, and we have CH3OH. I can tell A is out and C has to be the answer because these things, no hydrogen bond. Remember the requirement for hydrogen bonds? You must have a hydrogen bonded to a highly electronegative atom such as oxygen, fluorine, or nitrogen. Your hydrogen here is bonded to a carbon, not among that list. I don't even have to check for requirement number 2, which is the availability of the lone pair on the electronegative atoms. Okay, you should be able to draw the hydrogen bonding between the alcohol molecules to begin with, such as these. So I'm just abbreviating it like that. Show the lone pair, show the dipole, and then it will be from the lone pair of a neighboring molecule, like that. Okay, and then this is hydrogen bond. So my hydrogen bond is not drawn perfect like that. Ideally speaking, it should be around 180 degrees about the hydrogen. But anyway, I've got the dipoles. I should really draw the dipoles on the other alcohol as well. Not alcohol, sorry. I mean not water. I should have drawn alcohol and alcohol. Delta minus, delta plus. So dipoles, lone pairs, as well as label the intermolecular force. Okay, so the answer there has got to be C there. Question 6, very straightforward because they say bonding. Which type of bonding is never found in elements? When you think about all the elements you have, let me just remind you, such as group 1, group 2. Oops, I should really use the number system, but you could use the Roman numeral as well if you want to. So yeah, I mean, those are all metallic bonding. So, you know, giant metallic lattice. When you have the halogen, for example, you would have CO2, Br2, etc., etc. What you have is you have covalent, but you also have van der Waals forces because they are non-polar. They are simple covalent molecules, so they have got van der Waals between the molecules. What you cannot ever get will have to be ionic, because ionic, you must have a compound, you must have a metal and a non-metal, where you have, well, not necessarily a metal and non-metal, but you must have a cations, which usually come from the metal, as well as the anions, which usually come from the non-metal. But of course, we also have polyatomic ions such as ammonium, sulfate, nitrate, that kind of stuff. All right, so the answer there's got to be B there. Question 7 is a calculation question. So this is enthalpy changes. They have, these are not the usual formation, combustion, so we have to think carefully about this. Not to worry, so we just have to look at the equations and construct our own there's A2, construct our own Hess cycle, so not to worry too much there. They said it's Q kilojoule per mole. So what do we have? So enthalpy of solution, so they have given us enthalpy of solution, and they give us the enthalpy of hydration. If you look in the AS energetics topic, these are definitions you must know, and this is the kind of question where you say, but I never learned it before. It is in the syllabus, and if you never learned it before, you should have really gone through the syllabus fully before you're ready for a full pass year paper. Okay, so hydration means you take 1 mole of the gaseous cation, you dissolve in a large amount of water, so CS plus aqueous. Same goes with the Br minus aqueous. That is the hydration of Br minus. So that is going to be minus 335, and there is 1 of it, so you know, I just multiply by 1. On the other hand, for the cesium, there's also 1 of it, so there's 1 time minus 276. This is the enthalpy of hydration for the 1 mole of gaseous cations dissolved in a large amount of water to give you the hydrated cations. Okay, finally, I have the enthalpy of solution, which is to take 1 mole of the substance, dissolve in a large amount of water, such that I get substance dissolved in a large amount of water under standard conditions. So that is going to be plus 25.9, and that is multiplied by 1. So hopefully you can see the Hess cycle now. Hess law says the enthalpy change of a reaction does not depend on which path you take, whether it's direct or indirect, as long as you start from the same reactant and end out at the same product. So Q, which is going this way, is going to be this. So 1 times minus 276. Whatever is in the same direction, I'm just going to add it up. But this is in the opposite direction, so I have to go against this. And this is coming down is plus times that. So it's going to be minus 1 time plus 25.9. So this is the one where I take a minus, and then I just press my calculator. I got my answer as minus 636.9 kilojoule per mole, and that is going to be option A. Okay, but as we have any calculation, I think it's best if I just double check my calculations on my calculator, because you never know when you make a mistake. Yep, I got the same answer there. Question 8 is exactly what I was thinking about just now, which is like, you know, dealing with formation, dealing with combustions. So very direct, we can use the formula straight away. However, what they have given us is just a Hess cycle, so I can explain it in terms of the Hess cycle as well, because, you know, I'm not a one-tailed pony. I know exactly what is going on. So yeah, I mean, I don't just rely on formula without knowing where formula come from, because, you know, one day when you forget the formula, you can always go back to basic. So that thing there is the formation of CO2. So you are forming CO2 gas, and you're forming 1 mole of it, so it's multiplied by 1. But then you're also forming 2 mole of the water. So they say plus X, and hopefully you should be able to see that X is going to be the formation of H2O, but it's multiplied by 2 because you are forming 2 mole of the H2O. Okay, what else? You have the formation of CH4 there. Okay, This is the combustion of CH4 because I'm combusting or I'm burning 1 mole of the substance in excess oxygen under standard conditions. Okay, so what is the enthalpy change for X? Well, they said this is related like this, but I already said what is X. X is just X is in this direction, so this is a plus 1 time the formation of CO2. I know they haven't mentioned that, but it's actually 1 times that because I'm forming 1 mole of that, and it's in this direction. It's plus that. In this direction is going to be plus 2 times the enthalpy of formation of water, which means, you know, based on that information, therefore the answer must be D there. Okay, let me check. Plus 2 times formation of water. Yep, that is all right based on what I have just explained. So in this question number 9, we have these balancing equations. So we have copper reacting with dilute nitric acid, and what are we producing? We have this copper 2 nitrate, and we're producing water, and we have nitrogen 2 oxide. So this means the nitrogen is a plus 2 oxidation state, the oxygen is minus 2. This is a nitrogen monoxide, the other name is nitrogen 2 oxide. I can see the redox reaction here because if you look at the oxidation number, the overall molecule, the compound has 0 oxidation number, hydrogen is plus 1, nitrogen is what you want to find. You have 3 oxygens, the oxygen in the compound has a negative 2 oxidation number, so that is nitrogen plus 5. When I move that plus 6 and minus 1 to the other side, okay? This one is mentioned, there's nitrogen plus 2. What we have in the nitrate there, so let me just make that a bit clearer. So that thing is there. For the nitrate, we have copper 2 plus. We also have NO3 minus times 2. Therefore, I'm just looking at one formula unit. The oxidation state of the ion is minus 1 because it follows the charge on the ions. Nitrogen is what I want to find. I have 3 oxygens. The nitrogen is going to be plus 5 there. From here to here, it's not a redox because there's no change in oxidation number. But from here, the nitrogen plus 5, the nitrogen plus 2, this is reduction. There's a decrease in oxidation number. There is a decrease in oxidation number there. And what else? There's copper plus 2 there. And if I just use a different color, this thing is getting less and less responsive. Anyway, so there's copper 0 as an element. So there is oxidation of copper, so there is a plus 2 oxidation number, and the other one is minus 3 oxidation number from plus 5 to plus 2. Changes in oxidation number must be balanced, so I have to multiply that by 2, I have to multiply that by 3, because the lowest common multiple of 2 and 3, the lowest common multiple, LCM, is a primary school mathematics concept, so the LCM is just 2 times 3, which is 6. I need 6 electrons to be transferred throughout, and therefore the changes in oxidation number have to balance like that. If I see that times 2, so I can imagine that I need 2 of that, and I need 2 of that, therefore I need 2 of these. But I also need extra 2 of it, so I would say I will need 2 of it just now based on the redox. However, my nitrate is also forming the nitrate salt, so this is just an acid-base reaction, and therefore it is not involved in redox. I need 2 extra nitrate in addition to the one from redox, therefore I need 2 extra nitrate. Okay, so therefore it will not just be 2, it will be 4. Although I only use 2 of them for redox, but I need 2 more for that. Now the nitrogen is balanced, 4 nitrogens, then 2 nitrogen there. The copper, 1 of it and 1 of it, is it? Let me see. No. I need to times 3 there, so there has to be 3. And that doesn't look so right. Hang on, that should be 3, which means I need more than that. Just now, I only need 2 for that, but now I need 6 more nitrate. I need 6 more nitrate, not just 2 more. I need 6 more. Okay, because 3 times 2 is 6 more nitrate. In addition to the 2 unit which I need for redox, I have 8 altogether. Okay, so it makes sense that in my balance equations, I still have a balance the water actually, 8 hydrogens, so there's 4 H2O. This is now balanced. This equation is now balanced. So there's a mixture of both redox and the acid-base reaction to form the salt there. So just be very careful. And therefore, yeah, I mean, for 3 moles of copper, you need 8 moles of nitric acid, and therefore there's option D as the only correct answer there.